Beginning with atomic radii, as I previously mentioned, it is the only one that is different than the other three trends, so it's very important to remember. If you just remember the atomic radius, then you can remember that everything else is the opposite. Now let me just explain that really quick. So the atomic radius is basically the distance from the center of the nucleus to the outermost valence electron, right? If the atom was a circle or a sphere, the radii would be the distance from the center of that sphere to the outermost part of that sphere, all right? This is determined by the strength of attraction of the nucleus to its electrons. So if you can imagine more protons and more electrons, the larger the atomic radius would be. Okay, so as you move down along the periodic table, down in periods, of course the atomic radius is going to get bigger. Now you would think as you add electrons and protons, as you go to the right of the periodic table, you would think that the element would get bigger. But the reality is as you get more protons, the stronger the nucleus's charge becomes, and the stronger the pull it has towards those electrons. So actually, as you go left on the periodic table, the atomic radius gets bigger because the nucleus gets smaller, and therefore it is less has less strength. All right. So electrostatic attractions, Coulomb's law is that it is greater, the attraction is greater for more protons and more electrons, all right? And electron shielding can diminish this effect, partly explains consistency and size in transition metals, all right? So this is also determined by the principal energy level, meaning as you move down, the larger it gets. Therefore, the atomic radii will increase as you go from the top to the bottom and from right to left, which means all of the others that we're going to talk about go from left to right and from bottom to top. They all get larger. So ionization energy. The first ionization energy is the minimum energy needed to remove a neutral atom's outermost electron. For an element to lose one electron is called the ionization energy. This increases as you go from bottom to top and from left to right, as I mentioned, opposite of atomic radii. Now, so if you understand, metals lose electrons and nonmetals gain electrons. Why? Because nonmetals are to the right, so it takes more energy to remove or to take away an electron. Okay, I'm going to say that again. Metals lose electrons easier, okay, because they have a lower ionization energy, if you will, because they are larger in atomic radius, meaning the strength of attraction is less for those outermost valence electrons. All right? Electron affinity, also saying that as you move to the right and as you move up, elements have a stronger affinity for electron, which means the degree of attraction that an atom has for additional electrons. So again, its strength or attraction for electrons is stronger as it goes right. So if its attraction is stronger, right, that means that it is more likely to take an electron. Okay, so elements all the way to the right, like chlorine, fluorine, bromine, all those halogens, that group is called halogens. They have the strongest affinity for electrons. Okay? And lastly, electronegativity. Electronegativity is something that is very important to master the understanding of. Okay? It is basically what all the other the tendency of an electron to attract electrons when the atoms are bonded to other atoms. Right? This is very important in predicting how atoms combine chemically with each other. Chapter 6 and 7, when we talk about bonds, electronegativity is extremely important. Fluorine has the highest electronegativity at 4.0. And so in our book, we'll have an electronegativity chart where you can see the different electronegativities. Electronegativities are basically the strength of attraction from the nucleus to the outermost valence electron. Okay, so if you can imagine a larger radius or a greater distance between the nucleus and the outermost valence electron will result in a weaker electronegativity or a weaker attraction. Okay, the closer the electrons are, the stronger the attraction. Okay, And so basically, the strength of the electronegativity is based upon its atomic radius and is based on its number of protons. Okay? So it's important to understand, again, electronegativity, like electron affinity, and like ionization energy, electronegativity both increases as it goes to the right and as it goes up on the periodic table. Electronegativity would therefore decrease as you go down and as you go to the left. Okay? Before we move into the properties, right, the descriptive chemistry, all right, I want to just move over here and just answer a few questions. If I was going to ask which has a greater atomic radius, nitrogen or arsenic? Well, arsenic is below nitrogen, so therefore arsenic has a greater atomic radius. Again, which has a greater electron affinity, nitrogen or arsenic? Well, nitrogen is higher up, so nitrogen has a higher electron affinity. And then also left and right, which has a greater atomic radius, germanium or bromine? Well, germanium is to the left, so germanium has a greater atomic radius. Which has a greater electronegativity, germanium or bromine? Well, bromine is to the right, so bromine has a greater electronegativity. What if I switched the question? I said, which has a lower electron affinity, iodine or fluorine? Which has a lower electron affinity? Well, lower would be here, okay? Greater would be here, because electron affinity increases as you go up. Electron affinity also increases as you go right, okay? Only atomic radius gets bigger as you go down and as you go left. And there's some pictures in the book that show you all those different trends. Okay, so let's move forward into descriptive chemistry, right? We've already been through it a little bit, but this is the properties, and this is the last part of the chapter, right? Hydrogen is kind of by itself, combines explosively with oxygen to form water, given a sufficient activation energy, okay? All the hydrocarbons, okay, like CH4, all these, when they combine with oxygen, they create explosions, all right? Those are called combustion reactions. Alkali metals, this is group 1A, right, not including hydrogen. They're very reactive, violent reaction with water, soft. Examples are sodium, potassium. Group 2A, alkali earth metals, very reactive, but not as much as group 1A, includes calcium, magnesium, barium, strontium. Not as soft as group 1A. Demonstration would be hard water or burning a magnesium strip. You can look at both of those as YouTube videos, right? Demonstration of group 2 alkali earth metals. Okay? Transition metals, these are the B groups. These are your typical metals, copper, iron, gold. These are all good conductors of electricity. They're poor insulators. Okay? For example, when we, copper wire is good to use for electricity. So in your walls, you have copper wire inside of your, wiring of your house. Most likely it's copper. Okay? Transition metals are tricky to come up with properties. Why? Because there's almost just as many exceptions as there are trends. All right? Moving on, the intertransition metals. Most elements in the lanthanide series occur naturally. Most elements in the actinide series are produced in the lab. They're very dangerous because they're radioactive. When you see a little nuclear sign on an element, that means it's radioactive. Less than 1/1,000,000th of a gram can be fatal, all right, of the actinide series. All right, so very important to understand. Those are just some properties of those metals. Moving on to 3, 4, and 5A, group 3A contains aluminum and boron. Aluminum is very valuable until a process developed to separate it from its oxide. All right, boron is used in borax glassware. And I'll show you the little chart. This is just some interesting facts about each of these, but I'll show you a chart which says all the properties, and I'll post the chart as well. 4A contains carbon and silicon. Carbon is in everything that is living, right? Group 5A, phosphorus. Moving on, 6, 7, and 8. Group 6 contains oxygen and sulfur, all right? And group 7A, generally we would do demonstrations in class. We don't have that opportunity, so you can look those up. 7A, halogens, fluorine, chlorine, bromine. They're all very reactive, especially fluorine because it's the strongest. And when I say strongest, I mean the most electronegative. Lastly, the noble gases, these are, all these are happy. They don't need to change. They don't really like to bond because they all have 8 valence electrons. Okay, so I just want to move, so that's the end of chapter 5. Here's a periodic table that I like to use in the book. It's good because it shows you the electron levels, okay? Also, it says, you know, these orange are alkali metals, alkali earth metals, transition metals, and then post-transition metals, metalloids, nonmetals, halogens, noble gases. All right? But I do want to look here before we get into the periodic trends. This right here is the properties as I was mentioning. For example, that first group, alkali metals, they're less dense than other metals. One loosely bound valence electron, highly reactive, largest atomic radius, and low ionization energy, low electronegativity, of course, because it's all the way to the left. All right? So you can look through those. They're important to familiarize yourself with, okay? And I'd like to move into our periodic trends worksheet. Circle the element with the largest atomic radius and put a square around the element with the smallest atomic radius. Okay, so we have copper, potassium, nickel, and bromine. Okay, in order to do this, you must have a periodic table. Whoops. All right, so we're doing this first one. I'm going to let you do the others, but I just want to show you a largest atomic radius. Remember, atomic radius gets bigger as you go down and to the left. So copper, potassium, nickel, and bromine. So we need the farthest down and the farthest to the left. Let's look at our periodic table. Now, we know that, let's see, we have copper, Cu. Let's see if we can find Cu. There's copper. Ni, nickel. Here's nickel, so that's to the left of copper, so nickel would win that battle. All right. I saw bromine, which is here, all the way to the right of that. And we're missing one more. The last element is potassium. Now, if you look here, potassium is all the way to the left. So which has the largest atomic radius? The largest atomic radius, it says circle, and that's going to be potassium because it's all the way to the left. Put a square around the element with the smallest atomic radius. Well, bromine is the farthest to the right, so you'd circle potassium and you'd square bromine. So if I was going to go here and if I was going to do this myself, I would say square bromine, and then I would take a circle potassium. Not the best circle, but it works for the purpose. Okay, so that would be the answer to number 1, and you could continue on through the worksheet. Okay, for example, circle the element with the highest ionization energy and put a square around the element with the lowest ionization energy. So ionization energy gets larger as it goes left to right and larger as it goes bottom to top. So you could say the highest and the farthest right will win. Okay, so we know oxygen is to the right of beryllium. Oxygen is also to the right of carbon, but neon is higher up. Okay, whoops. Neon is neon is farther to the right as oxygen. Now, generally you would say, okay, it must be neon, but neon, so the highest ionization energy, meaning the most energy to remove an electron, generally we don't include the noble gases in our ionization energy, electronegativity, and all those, but you could say neon, right? You could also make an argument, right? It says explain why you made these choices. You could say neon because it's the farthest right, okay? But you could also say oxygen, okay? Because neon is a noble gas, and so we don't deal with ionization energies for noble gases, whereas oxygen is the farthest right, aside from neon, which is a noble gas. I would be okay actually with either answer, and you must remember that beryllium is all the way to the left, so beryllium, of course, being here, would be the lowest ionization energy. Okay, make sure you really can master those periodic trends. We're going to talk about it some more tomorrow and go through it. Yeah, if you have any questions, feel free to reach out.